Today, it's an oldie but a goodie. We're going to be looking at C programming. Stay tuned. Hi, I'm Mark Lassoff from Framework. I produce content that teaches web and mobile development and digital design. Today, I've got a really exciting and kind of unusual video for you. We're going to be taking a look at the C programming language. Now, I know the C programming language is old school, but C is the basis for just about every language that we use today, and it's useful to know. Before we get started, if you enjoy this type of content, do me a favor, hit that like button and subscribe. That's going to let other people know about our channel so they can take advantage of this training. And now, let's get started with the C programming language. Before we can start coding in C, we need to set up our environment. Now, I've created this video especially for Mac users. So the good news is, if you're a Mac user, it's pretty easy. We're going to be using, first of all, our terminal, but we're going to have to install the C compiler first. You may already have it installed. I'll show you how to check. And then we're going to be using as our text editor Visual Studio Code and its C and C++ plugin. Let's get started. In order to see if your computer is set up to read and compile C code, you need to go into the terminal. If you don't know how to reach your terminal, the easiest way is to go into Spotlight and type terminal. You're going to run the terminal program, which looks like this. In order to see if you have the C compiler, you can type gcc --version. If you have the C compiler, you should see a similar message to the one I have here, which indicates the version of the C language that's installed. Your version number may differ slightly from mine, and that's okay. If you see a message that indicates that you don't have the GCC compiler installed, you can Google search for instructions to install the compiler yourself. You also can install it by installing the Xcode command line tools, which is Apple's development environment. Either way, it's pretty easy to get these installed and start coding in C. The other recommendation I have is to install Visual Studio Code. This is a free code editor that's available. Just Google search Visual Studio Code and download and install it. It's available for Mac, PC, and even Linux. Once you have the code editor installed, I'd like you to click here on the left-hand side in the extensions and search for the extension for C and C++. The extension looks like this, and once you have it, you can go ahead and install it into the editor. What that's going to do is it's going to give you code completion, debugging, and other support for C and C++ that's not native to the Visual Studio environment. In the editor, you're simply going to type your code in the code window, and you can actually use the terminal below to execute your code. I'm going to go ahead and create a new file, and I'm going to save this as a C file. So let's choose File, Save As, and I already have a folder for my C code. I'm going to call this hello world.c. Now I can actually type the code for my first C program. C is a pretty bare bones language, so we actually have to include a set of tools for standard input and output, stdio.h. That includes the header for the standard in-out or input-output library. That'll allow us to do things like print to the screen. C starts executing in a main function. So the way we write that function is like this: int main, and then open parentheses. You'll understand more about these functions a little later in the video, but what this means is this function returns an integer. The function is called main, and the empty parentheses indicate it doesn't take any arguments. Now, since this particular function is designed to return an integer, we should return something, so we'll end with return 0. Now all we have to do is write some code that outputs something. I'm going to use the print function, hello world from C. The print function takes as an argument this string, hello world from C. So what I want to do now is save this particular file. Since I've already created a file name with .c, all I have to do is hit File and Save. We've written and saved our first program using our text editor. Now, we're going to actually execute the program using the command line. I really like executing programs on the command line. It makes me feel really old school, like I'm using text-based computers back in the 70s and 80s, because they did it the exact same way. All right, let's turn to our terminal and run this program. Executing a C program is a two-part process. We're in the correct folder, so now we're going to compile the file into an actual executable. Right now it's a text file, and the C interpreter can't read a text file. We've got to compile it into machine language. So we'll do that with GCC. The file we want to run is compile is hello world.c. And we want to make an executable, which I'll call hello world. And after a moment, it doesn't look like anything happened. But if I use the list command, there you can see we've got hello world.c. And we've also got just a plain old hello world. That's our executable. I'm going to run that by hitting the dot, the slash, and then the name of the file. There's no .c there, so I'm just going to run it like that. And there you can see the program executed. We got the text, hello world from C. If we were to make a change to the program, for example, add another line of output. I'm going to add a \n for a new line here, and then we'll print again. My name is Mark Lassoff. Not very creative, but it'll do the trick. So I've got to recompile the code in order to run this again. This way the executable will reflect the new line of code that I've entered on line 5. Let's go ahead and use our GCC command again to compile what we've got. And now if I run it by running the executable, we have both lines of output. In this part of the video, we're going to learn how to declare variables. Now, I know a lot of you are coming from JavaScript, where you just declare a variable with the keyword var. It's not quite the same in C. The reason for that is in C, we're directly allocating a specific amount of memory with our variable. Some types of variables use very little memory. Others will use a whole chunk. So I'm going to show you how to declare your variables by type, and by extension, allocate the correct amount of memory for the variable. So there's actually two steps to creating a variable in C. First, we have to declare the variable via its type. So let's say our first variable we're going to create is a char variable or a character variable. And then we got to give it a name. I'm just going to call this one X. Now that we've declared it, we can assign it an initial value. Since this is a char, it's got to be a character. So let's say X equals M. So the two-step process is, again, I'll use comments here which are ignored by the C compiler. Declare the variable by type, and then initialize the variable with a value. So now we have that M in memory. We can also declare multiple variables at the same time. So we could declare Y and Z, and then initialize those separately. So Y equals, again, a single character A, and Z equals, again, a single character L. Character variables are one type of variable we can declare. Integers are another. So let's say int age, that's a much more descriptive variable name, 47. Notice there's no quotes around the numerical values. And I also combined my declaration with initialization into one step. So this is combined declaration and initialization. You'll see that pretty frequently because it's just one less line of code that you have to write. In addition to integers, we have floating point numbers. A floating point number might look like this, and then we can initialize it, f indicating the float there for a floating point number. Doubles are floating point numbers with more precision. So I'll call it exact, and we'll say 2 point, I don't know, a whole bunch of values there. And that's a much more exact floating point number. If you think about it, an integer probably requires less memory than a floating point number in most architectures because it's less precise. At the same time, a double requires double the memory of a regular floating point number because it has more values and is even more precise. So these declarations are about C providing the correct amount of memory to store these values. I like to think of this like moving and moving boxes. If you've ever moved, your whole life becomes about boxes, and you want to get the right size box for the right size stuff. Well, when you declare a variable, you're declaring a box of specific size, a certain amount of memory to hold the values of that type. An integer has a range of values that it can hold, and therefore a specific amount of memory is allocated for an integer. So I like to keep that comparison in mind. Right size box for right size value. So now we have a bunch of values stored. We have X, Y, Z, age, GPA, and exact. If I want to use these variables in a printf statement, I can do that. The value of X, now again, that's just a string that's going to be output, but here I'm going to put %C, comma, and then X. And you'll recall that X was the first variable we declared. I can do the same thing with Y and Z. So printf, the value of Y, and again, %C is our character entity. That's where the actual value is going to go. The value is going to be substituted for that %C, C being a character entity for a character or char variable. And then the final char value, which is Z. Again, %C, because it's a char, or character variable, Z. So that's going to retrieve the values stored in X, Y, and Z. Let's go ahead and compile this. This is called variables.c. So GCC, variables.c-o, and we'll simply call the executable variables. All right, no errors, that's good. So now we should be able to run this with /. And there you can see the value of X, the value of Y, and the value of A. What I didn't do there was use new line characters. Let's recompile it with the new line characters so our output looks a little bit better. I'm just going to use the up arrow to find the previous command. We'll compile again, and we'll run the new executable. That looks a little better. The value of X, the value of Y, and the value of L. So we've been able to retrieve the char values, but what about the integers and the floats? Well, print \n, mark is %d for integer, years old. And this time the variable is age, so that'll make that substitution. Let's do the floating point variable. Print, again, we'll start with the \n. My GPA in college was, since this is a float, %f, comma, and we're going to use GPA. All right, let's save these new changes, and let's execute again. We have to compile first because our source code has changed. Looks like we've got an error here. Printf declared here in int. Let's see where our error is. And I see it, just a typo. Instead of printf, I just typed print. And by the way, these errors are pretty helpful because they tell you exactly what's wrong here. It even says here, note, did you mean printf? So I was able to look at that and know exactly what I did wrong. All right, let's go ahead and try and compile again. No errors this time. Let's run our executable. And there you can see Mark is 47 years old. My GPA in college was 3.17000. It's actually giving us all of the precision available in the floating point number. We can change that if we want to for less precision. So let's change this to 0.2F. Let's compile again. And there you can see we get 3.17. The only other change I want to make is just eliminate that space there in the string, and now everything will come out just perfect. All right, so we've declared variables, we've used character entities to output those variables, and we've used both integers and floating point numbers. Sometimes you want to hold a value, but you want to ensure it doesn't change through the life of your program. Instead of calling this a variable, we call this a constant because its value is constant. We're still going to be interested in the right size or the right amount of memory being allocated for the constant. But we know that if we try and change the value of a constant during the life of our program, we're actually going to get an error. All right, let's take a look at constants now in C. C creates constants using a preprocessor directive called define. So we could define, for example, length at 10. We could define width at 25. And we could even define new line as \n. What's going to happen is anytime that the C processor encounters one of these constants, it's going to substitute the value. So let's, for example, declare a variable, an integer called area, which will be length times width. And let's initialize it with length times width, using the constants in our preprocessor directive. Area equals length times width. By convention, our constants are going to be in all capitals. All right, so let's print out the results here. So we'll use printf. The area is, and since this is an integer, we're going to use our friend %d, area. All right, looks like we've got everything here. Let's go ahead and compile this using GCC. It's called constants.c. We'll just make our executable be called constants. Compiles no problem. And there we get the area is 250. So that worked just fine. Since new line is a character, we could use that constant as well. Let's say roses are red. So %c for character, and then new line. Roses are red, violets are blue. Again, character entity %c. New line is our constant. Let's recompile and test. No errors on compilation. And there you can see we got roses are red, violets are blue. Probably want to add one more new line in there. I'll add it just here. This way the area and the poem are on separate lines. And let's recompile for the last time. And that looks great. Perfect output. I know what you're thinking. I suck at math. Doesn't really matter. What we're going to be doing is using the mathematical operators to perform the math for us. C is very good at math and very fast. So let's take a look at the different arithmetic operators that are available to you in the C programming language. In order to demonstrate mathematical operators, we need to have a few values in memory. So let's declare a couple of integer numbers. We'll call them x and y, and one floating point number, which we'll call z. We'll initialize these. We'll give x an initial value of 25, y an initial value of 37, and z an initial value of 42.15. So now that we have some numbers, we can actually start using our arithmetic operators. The first one will be addition. And what we'll do is we'll simply add x and y and output the result. So since this will be an integer, we're going to use %d. And then we'll simply use x plus y here. So the plus in that expression is our operator, and it signifies addition. Let's save at this point and just take a quick look at the result. So I'm going to use my GCC compiler. This is called arithmetic.c, and we're going to output it as arithmetic. Okay, we didn't get any errors, so let's give this an execute here. And there you can see x plus y equals 62, which to my non-mathematically oriented brain looks correct. Let's do subtraction. So the mathematical operator for subtraction is minus. And we'll simply do x minus y equals. And again, this is going to be an integer, so %d, and x minus y. Again, minus there being our mathematical operator. Okay. Looks good to me. Let's do multiplication and division, which I imagine are as you expect. So x times y. And again, that's going to be a integer. And we use the asterisk for multiplication. All right, and division. So we use slash as our mathematical operator for division. And even though this would typically give us a floating point number, because both x and y are integers, it's going to give us an integer in return. And let me put in my \n so that's a little clearer. Should have remembered to do that before. Okay, and let's take a look. Compile and run. And there you see the results. Now, the result of the division is not what you'd expect because we're getting a 0. And again, that's because we're taking two values that are integers and dividing them, so we have to get an integer result. Let's fix that. So what I'm going to do is I'm going to create a double variable called result. That'll hold the result of x divided by y. And I'm going to cast x divided by y as a double just like that. So what that's going to do is it's going to give me the result of x divided by y as a double, which just remember is a double precision float, and stored in that double variable result. Let's change this to a float, and let's put result right here. Okay, so now that we have that change made, let's GCC our program to compile it, and let's run the executable. And now you see a floating point result .67567, etc. for our division that looks a lot more reasonable. Now, if we're dealing with floating point numbers to begin with, then this becomes a little bit easier. Make that printf so it compiles correctly. We'll compile again, and let's run the executable. And there you can see we get the result for x divided by z without any casting because z was a floating point number to begin with. Couple more mathematical operators you should know about. So I'm going to run the command x++. That simply increments x by 1. So now if we print out the value of x, and it's still going to be, of course, an integer, watch what happens. Compile, run our code, and notice it says x is 26. If we scroll up, the original value of x was 25. If we change this to x minus minus, that's the decrement operator. That'll subtract 1 from x. So if we compile this again, the result of x now will be 24 because we've decremented x. So plus, plus, and minus, minus are increment and decrement. And the last one that I think it's important to know about is what's called modulus. And that's essentially the remainder after division takes place. So that's a % sign. Let's create a new variable integer. I'm going to call it mod result, and let's do 9 mod 2. So here, 2 goes into 9 4 times, and the remainder is 1. So our mod result should be, again, an integer mod results. Okay, so that should show us what the result of the modulus operation is. We have compiled, and looking at the last line here, mod result 1. Let's change this. Let's say it's 47 and 7. So again, we're looking at what the remainder is after division takes place, mod result 5. Because 7 goes in evenly 6 times, giving us 42. 47 minus 42 is 5. In addition to arithmetic operators, we have logical operators. Logical operators allow us to make comparisons that are evaluated as true or false. So those comparisons are equal to, not equal to, greater than, or less than. When we make those comparisons, the expression is evaluated as true or false. Let's take a look. I've already written the code that will allow us to demonstrate our first operator. Inside our main function, we declare x and y, x holding the integer 10, y holding the integer 20. Line 6 is the key line here. If we look on the right side of the assignment operator, you see x equals y. Here, equals is the operator we're interested in, and it's looking for equivalency. Since x is 10 and y is 20, here, what's stored in the result will be false, or 0. So when we output the result, x equals y, we're going to output a 0, indicating that's false. Let's go ahead and compile and run this. And there you can see x equals y is 0. Let's change up results, though. Let's change up results, and this time make it something that is true. So in this case, x is less than y. So there's our comparison. So this should result in true or 1. So again, we can compile and see the result. And x is less than y, well, that's true. If we did x is greater than y, that's again going to be false, right? Because x is not greater than y. 10 is not greater than 20. So we get our resultant 0. If these numbers were the same, x and y were 20, and we did, for example, greater than or equal to as our operator, so now that's a true statement again. And if we compile and run, you'll see we get 1. So these operators are going to become really important when we do conditional statements that are coming up. Now that we've got our operators down, it's time to look at conditionals. Conditionals are how a program makes decisions. Decisions in programming are based on whether or not something is true. And they read basically like, if this is true, then execute some code. It sounds pretty simple, and it is. Let's go ahead and have our program make some decisions in C. The decision we're going to have our C program make is whether or not someone is eligible to vote. If we simplify things a bit, someone is eligible to vote if their age is greater than or equal to 18. In this case on line 4, I've declared an integer variable assigning the age the initial value of 22. Our test, however, in our conditional is going to look like this. Age greater than or equal to 18. If that resolves as true, then we're going to execute what's inside these curly brackets. So I'm going to use the printf command and simply output you are eligible to vote. If the conditional does not evaluate as true, then the code on line 6 will not be executed. In this case, I expect it to be evaluated as true because 22 is greater than or equal to 18. Let's compile this, and we'll make the executable called conditionals, and then run the executable. And there we get the result. You are eligible to vote. Let's change our initial age value to 17. So now the initial condition will fail because 17 is not greater than or equal to 18. We have to recompile, and let's test, and we get no result. No result is not a good way for the program to indicate that someone's not eligible to vote. So I'm going to add an else block. The else block runs if the initial condition in line 5 is evaluated as false. So here we'll put, you are ineligible to vote. If I save and we run this again, knowing the initial condition will still be evaluated as false, we should see you are ineligible to vote. And we do. That's our output, because 17 is not greater than or equal to 18. Now, this is a fairly simple conditional. We can also have more complex conditionals that test for multiple conditions. So I'm going to declare another variable called citizen, and I'm going to assign its initial value 1. Since there's not a Boolean or true-false type in C, we can use an integer with 1 representing true and 0 representing false. I'll just put a comment here so we remember. So now both of these have to be true. Age has to be greater than or equal to 18, and citizen has to be equal to the value of 1. If either of these conditions is not true, then the statement will be evaluated as false. So let's make this so both will be evaluated as true. Age equals 18. Now age is greater than or equal to 18 is true, and citizen is true. So we should see you are eligible to vote. We'll compile. You are eligible to vote. That's great. If citizen were false, however, the whole statement would be considered false, because if you use an and, then both sides of the conditional have to be true in order for it to evaluate as true. So now, because our citizen is set to false, the whole thing evaluates as false. Let's look at a second example. I'm going to set an initial variable as an integer with a grade equaling 81. This represents a grade on a test. And then a char variable for letter grade. And I'm going to initially not assign that a value. And what we want to do is figure out what will the user's letter grade be based on the integer grade. So if grade is greater than, let's use greater than or equal to 90, then letter grade is going to be A. Now we have to do an else here, and the else is going to be followed by another if. So else if grade is greater than or equal to 80, right, then the letter grade is going to be a B. We'll continue our else ifs, and I'm going to use a little copy and paste here so I speed that up. So the next one, if grade is greater than 70, then we have a letter grade of C assigned. If greater than 60, then a D is assigned. And finally, if it's none of these, then unfortunately, the letter grade is going to be an F. So the last thing we want to do before we exit out of the function return 0 is print out the letter grade. And we're going to use character there, and letter grade is what we're outputting. So let me save this second file. I'll call this conditional2.c. And so now we have a more complex conditional. But what happens here is it's going to test only as many of these else ifs as needed till one of them is true. Let's go ahead and run this. So it's going to be conditional2.c, and I'll make the executable just conditional2. All right, no error. And there you can see letter grade B. So now we're actually able to write programs that do something pretty useful, because here we have a kind of long, more complex determination based on our ifs, but we're still getting the correct output. In C, functions are essentially blocks of code that have a purpose to execute some part of your larger program. You've actually already been using a special function called the main function. That's where the C processor knows to start executing your program. Now, we're going to write our own functions. We're going to write functions that execute on their own when called, that take arguments, that take in values, and also functions that return values. Let's take a look at the code. As I mentioned a moment ago, we've been using functions the entire time we've been writing C code. I just haven't talked very much about them. The function called main is where C knows to start executing your program. The main function itself starts with int because it returns an integer. It has the word main, which is the name of the function, and then in the parentheses, it receives no parameters. Nothing is received by the specific function for it to work on. We can write other functions in our code. For example, let's write a very simple function that greets the user. Our function will return nothing, it'll be called greet, and it'll receive no arguments. So there on line 3, I've declared the function. You should declare the functions you're going to use before your main, and then you can write the fully implemented function afterwards. Void, greet, so same as the declaration, but here we're going to put the code that the function runs when it's called. Our function simply types out the word greetings. Now, if we ran this right now, it would compile, but it wouldn't actually do anything, because while we've written both the declaration of the greet function and the implementation of the greet function, we haven't called the function anywhere and told it to execute. We'll do that on line 6. So now when line 6 is encountered, it's going to call the greet function and execute the code inside the greet function, which is on line 11. Let's save and compile and see how it goes. So this is called functions.c, and our executable will just be called functions. And there you see we get the greetings. Now, of course, we can call functions as many times as we need to or want to. So here we're actually going to run the greetings function 3 times because it's being called on lines 6, 7, and 8. And there you can see greetings, greetings, greetings. Just to make our output neater, I'm going to add my \n here. So on line 12, we have a very, very simple function because it doesn't return anything and it takes no parameters. Let's write a function that actually takes parameters. This will be a little more interesting. So our function will still return nothing, but it will take 2 arguments. We'll call them int x and int y. So there is our declaration. After the declaration, we'll need an implementation. And again, the first line is going to be the same. Void, multiply, int x and int y. And now we can implement our function. So let's create result, and result will be x times y. It'll hold that value. And we'll simply print out the result is for our integer. So what's going to happen here is values will get passed into multiply. We'll declare the result variable. Result will be assigned the value of x times the value of y, and then we'll output the result. What you're probably asking here is, well, how do we get the results into multiply? Let me show you. We don't need these 2 anymore. So we'll call multiply, and we're going to pass it. Notice here, by the way, my environment knows that we're expecting an integer x and an integer y. That little box pops up to help me. So let's say 15 and 23. So again, when line 8 executes, the 15 will be passed to the multiply function and assigned to x. The 23 will be passed to the multiply function and assigned y. All right, so now we have our function call. Let's see how well this works when we compile and run it. And there you can see the result is 345. So it's giving us a result by taking the values from x and y and multiplying them together. Let's try some different values, 25 and 167. We'll save, and let's execute it again. Compile, run, 4,175. Looks like that's working fine. Let's try one more. So let's do a function that gives us the square of a number. So void square. This is only going to take one number. It's going to be an integer, and we'll call it integer z. We could reuse x here because we're using it in a different context, but I'm not going to. And now let's write our square function. Again, void returns nothing. Square int z. And what I'm going to have this function do is simply multiply z by itself. And I'll have it do it in the output here. The square is, and this will again be an integer, and it's going to be z times z. And we know that that math will happen first, and then the result will be printf'd out. We need our call here in main, so we'll square the number 82. So that'll call the square function. It'll pass the value 82 and assign it to z, and then print out the result. Let's again compile and run. And the square is 6,724. I always forget my \n's to keep the output neat. Let's square a different number. Let's square a number 417. Okay, so that will change our output a little bit. And there we get 173,889. Now, let's also write a function that returns a value. This will be a little bit different. So let's go ahead and write a function that calculates a batting average. Float, because it's going to return a floating point number. Batting average, and it's going to take 3 arguments. It's going to take a number of at-bats. It's going to take a number of hits, and it's going to take a number of walks. So this is a little more of a complex function, but same principle. It's taking 3 different values, and it's returning a single floating point value. All right, so let's write our signature here. So again, at-bats, hits, and walks. Of course, on line 6, we've declared the function. Now we're actually writing the function implementation. So I'm going to declare a variable called batting average, which will be a float. And batting average is going to be equal to, as an initial value, casted as a float, right? Remember, we have to cast it as a float. So I believe the formula is hits divided by at-bats minus walks. And that math has to be done first, so I put it in parentheses. I'm going to add some spaces here just to make that a little clearer what's happening. Now, instead of outputting the batting average, I'm going to return the batting average. That's our floating point number. That's going to be returned to where it's called. Now, you may be a little unclear what it means to return it. Well, watch how I use this. Let's go ahead and declare a float. BA is going to be batting average, and we'll pass a number of at-bats, let's say 450, number of hits 99, number of walks 35. I have no idea if that's going to turn out to be a good batting average or not. So now what's happened is the values 450, 99, and 35 will be passed to the batting average function starting on line 16. The math will occur within the function, and then whatever batting average turns out to be, that float will be returned and assigned to BA. We could then print out the result here. The batting average, which is going to be a float, and BA. Now, don't get confused, because these variables are only visible or are only valid within the function within which they're declared. So this batting average variable on line 18 can only be seen within the batting average function. The returned value is then assigned to the variable BA on line 12. Let's try this out. All right, so it compiled. So the batting average is 238,554. A batting average really should be 3 values. So let's just change this up to 0.3F. Let me change the numbers too. Let's say he had 500 at-bats, 131 hits, and 25 walks. Let's see what that batting average is. Again, we have to compile and run. That batting average turns out to be 276 and is now correctly formatted. Keep in mind that these functions are more useful if they take parameters and return a value. This batting average function that I just wrote on line 17 can be used again and again in a number of different programs, because we know what parameters it takes and it returns the value. There's no specific implementation with what we do with the return batting average value. For example, our program could put it in a database or display it on a large screen within a stadium or many other things. It doesn't necessarily have to just print it out to the console. That's what we're doing with it, but we don't have that implementation in our function, making our function more transportable. Okay, so we've looked at functions that do not take a value as a parameter. We've looked at functions that do not return a value. Then we've looked at functions that take a single parameter, multiple parameters, and return values. Thanks so much for watching. I hope you enjoyed this video on the C programming language. Realize that we're just scratching the surface. There's much more C you can learn and much more you can do with it with practice. I do hope this video gave you a good start. If you enjoyed this video, thought it was useful, don't forget to leave a like and subscribe to our channel. My name is Mark Lassoff for Framework Tech Media. Thanks so much for watching. I'll see you next time.